Hello, everybody. We're from the race car course. We are the race car boys. Today, we're going to be presenting Project Apex. This is our Explore project, and we got to independently choose what we wanted to work on. And all of us being interested in racing and Formula One, we decided to choose this. I'm Daniel. I'll let some of the other team members introduce themselves.
I'm Bebas.
I'm Davil.
I'm Alexander.
So our fundamental idea for this project was we wanted to create a custom racetrack and model a Formula One car in the Unity simulation. Afterwards, we wanted to create an artificial intelligence driving software that would use a documentation lab to generate a racing line for the AI to follow as it raced against the user. The documentation lab measures and stores the corners and turns of the specific track, allowing the code to be adapted to different racetracks. The vehicle uses LiDAR to avoid collision and detect corner information by tracking the walls adjacent to the track. The car moves slowly through the documentation lab in order to gather detailed information about the track.
So one of the challenges we faced while creating the racing software was the LiDAR cannot see farther ahead and determine the bend of the road, meaning that the car cannot anticipate the direction of the corner until it's already entering the corner.
We also had a lot of difficulty and learning curve using Unity. So for all of us, we had never used Unity before, and we learned quite a lot of things. So this was actually our second car model. We were using a McLaren model previously, and we eventually found this model. And after painstaking hours, we were able to separate the wheels from the model and merge them with so-called wheel colliders in Unity. And that's what allows the wheels to actually spin on the model and the front wheels to turn. There was a lot of other physics that we had to tune. So the wheel colliders have slip on them. So you have asymptotal slip and extremal slip, forward and sideways friction. So that's something that took a lot of tuning. And we actually ended up getting it pretty close to a real Formula One car. So that if you floor the car, it'll just burn out. It doesn't have enough traction to go. And occasionally you can get it drifting through corners. So those are just some of the things that we did to kind of more closely model an F1 car. And as you can see, we have a beautiful track modeled, as well as a Red Bull car, which is a very nice F1 model.
So for our approach for the racing software, the documentation lab provides the car with information about curvature and corner distance through vectors formed by the steering angle and the distance traveled at the angle, which was calculated from speed times time. Then the racing code utilizes a state machine and alternates between different driving states based off of different track conditions. The car detects the corner and its apex by comparing adjacent frontal area LiDAR scans with each other. An abrupt difference in the LiDAR reading signifies an upcoming turn. After detecting a corner, the car would pair the corner with data gathered from the documentation lab and apply minimum curvature trajectory planning to the data to generate the most efficient racing line by minimizing the squared sum of the curvature values. The new trajectory allows the car to enter the corner from the opposite side and aim for the apex. This is a line commonly used by professional racing drivers. The ultimate goal of the software is to minimize wheel churn in order to maintain the highest corner speed. However, we weren't able to complete the racing function due to lack of time, but we had successfully created the documentation software, and the car has the full capability to map the racetrack. In the future, we will continue to complete this software and make sure our car races well.
In terms of real-world applications of our software, our implementation is actually quite similar to how similar autonomous racing systems, such as RoboRace, actually operate. However, unlike RoboRace, we're only using LiDAR, while RoboRace tends to use more sensors like radar and AI cameras. Our car is capable of adjusting if necessary to a vehicle that's side by side, which makes it effective for real racing, as it's able to defend its position. In future implementations, use of color cameras and computer vision could make our application work on more than strictly walled circuits, as it would allow us to detect curves and track limits using image processing. This would make our program applicable in a wider variety of race courses, not just ones that are specifically designed for our program. In addition, the use of a more advanced state system with passing and defending states would make our simulation more realistic, as it would be able to fight back more and push harder.
Yeah, and as for where we're going in the future, we're actually really happy with how this has turned out. we took this stock race car simulation software, we put this, Red Bull model over it, and we have this beautiful racetrack. So we have a lot of features actually that we're still looking to implement in the software. We have good traction control and good slip control. We have a actual steering wheel inside the car that moves with the wheels. We're going to be implementing different camera views, engine sounds, as well as a multiplayer mode where you can race against the AI. And overall, it's been really fun, really interesting, and I think we've all been really happy with how this turned out. And it's just really fun to play. Honestly, racing against the AI is a great time, and it's super cool to see the simulation software take on a different light. So yeah, I think that's all for our presentation. Thank you for your time, and we'll pass it off to another group. Thank you.